Okay, so what I want to look at right now are some more applications. Now we've seen, and I should say real world applications. One could think of arc length and surface area as applications, but they're really sort of math. They're very mathematical. It doesn't really feel like the real world, at least not to me. So right now we're going to go do some more real world applications. We've done some of these. We've seen some of these before. We saw the basic idea of work. We saw the basic idea of, for example, if you know position, finding, if you know acceleration, finding position, for example. So that was just the very basic idea of thinking of derivatives and antiderivatives and understanding what that means. Understanding integral is an antiderivative and just going, as I like to say, up the ladder or down the ladder. Okay. So the applications we're going to look at now are a little more advanced because it's not quite as straightforward as simply saying, I've got a rate, I'm going to take the integral, and it's going to give me the amount, which is the thing that we've basically done before. So the first application, in these applications, we're going to be using integration to interpret a situation. In the same way that to find surface area, we used integrals to interpret what was going on and do the calculation. In the same way here, we're going to use integration and then interpret the results. Okay. So the first application I want to talk about in this way is from economics. And the topic that I want to talk about is consumer surplus. So first, I'm going to give you a 2-minute lesson on economics. Okay, so here we go. So suppose you value an item at more than you pay for it. That's great, right? So what is this? So what does this mean in economics? How do we measure this? Suppose my value for a shirt is $35, but you can buy it for $27. So if you buy 30 shirts, what's your quote-unquote benefit?
$90.
Right.
Is it 90 times 8 times 30?
Right.
$8 per shirt.
Oh, not
So the benefit on the quote-unquote benefit on each shirt is $8. You get 30 shirts, so the benefit is $240. So this is called the consumer surplus. So that's the basic idea of consumer surplus. Pretty straightforward. Let's make it a little more interesting. So in a market, different people place different value on an item. Or at least a different price they're willing to pay. This creates what is called the consumer demand curve. So what happens? So mathematically, we say that P, which is the price, is P of X, where X is the number of items that are sold in the market, and P is the price it will sell for as determined by how many people will buy it at that price. So for example, if I sell a car for $30,000, only a certain number of people will think it's worth that and will buy it at that price. But if I sell the car for $20,000, a lot more people will think it's worth it, or at least will be willing to pay that price, and I'll sell a lot more. And that's the idea. So we're just going to use some really simple functions for this. So let's say that P, the consumer price function, is 100 minus X. So for example, if the market price is $35, how many items get sold?
So the consumer price is the price that the consumers evaluate at that?
The price is the price. So 65 items get sold, because 100 minus 65 would give you $35. Okay. Now, other way around, if 40 items are sold, what is the market price?
60.
Right, and how do you know that?
Because we use the item number determined by X. It's X value. So.
Right. So 100 minus 40 will give you 60. Right. Now, there's naturally a lot more fancy economics. We could talk about, this is consumer demand. We could talk about supply and all those sorts of things. If you take an economics class, that's what you'll do. But I want to look at, like I started, I want to talk about consumer surplus. So here's where we start talking about consumer surplus. Note that lots more people would pay more than $60 for the item. So for example, if one item is sold, then the price is $99. So that means that there's one person out there in the market who would actually pay $99. So what's that person's surplus? At $60, that person's surplus is $39. And then you can go ahead and think about what about if there were, if the price was 95 or the price was 90, da 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 da. You could figure out what's the surplus of all these things. So, call the market price P. The consumer surplus is every individual surplus, and you have to add them all up. So what's an individual surplus? It's whatever the prices they're willing to pay, which is P of X, minus the price they're actually paying, which is capital P. Now, of course, this is harder than the original problem, because in the original problem, we just said everything is fixed. But now we know that P of X is a function. It's changing. So if we have something that's changing, and we want to add them all up, what do we have to do? This becomes an integral. And you could see, hopefully by this point, you could see the way that thing becomes an integral. How does this become an integral? What's the integral going to be?
The sigma, instead of the sigma sign, it's going to be the integral sign.
And there's the definition of consumer surplus.
One useful.
Yeah. Okay. So, to take that last example, what is the consumer surplus in that situation if the price function is 100 minus X and 40 items are sold?
100 minus X minus 40. Integral of.
So it's the integral of what?
Should be
100
from
minus
0
X
to
minus 40. Yes.
Should it be from 0 to 40?
And it should be from 0 to 40. Because those are the items that are getting sold, going from 0 to 40. So,
Wait,
consumer surplus.
Why is it minus 40? Because it's 40 items, but we're subtracting minus. It should be minus 60.
You're exactly right. Because what should we be subtracting?
100 from we should subtract.
Right.
40.
We should be subtracting the market price P. And when 40 items are sold, what's the market price P? 60. Exactly. Okay. So remember, one thing is the number of items sold, the other thing is the price. So check that. Okay. So we just simplify this. This is 40 minus X dx. So naturally, once you have this set up, nothing in this particular problem is so difficult. This is, I think, hopefully a pretty easy integral to do. So 40x minus x squared over 2 from 0 to 40.
P of x minus p at x. Essentially.
You could think of it that way, yeah. Okay, so this gives 1600 minus. You know what? Let me just write this out. This is 40 times 40 minus 40 squared over 2 minus 40 times 0 minus 0 squared over 2. And you work that all out and you get 800. Okay. By the way, 800 what? What are we counting in this problem? This is $800. Exactly. Okay. So on the one hand, you can just memorize the formula. It's the integral of the price function p of x minus capital P, the market price, dx. On the other hand, remember what it is that the integral represents. It's the sum or the accumulation of every individual's surplus. And every individual surplus is the price they're willing to pay, which is little p of x, minus the price they're actually paying, which is capital P. So because of that, this is a side note, you could actually think of this in the following way. You could think of p of x minus p. It's the surplus, that's the surplus for each item. So for example, for the first item sold, there's a certain surplus. For the second item sold, there's a certain surplus, et cetera, et cetera. So in a sense, this is the surplus per item. It's a rate. So you integrate it and you get the total surplus. Now, this is a much trickier way to, this is a very complicated way to think of it as a rate. It might be easier just to think of it in the old way, that you're adding up all the individual surpluses. So we got that. Okay. Yes. But that does bring up a good point, which is a really useful way to interpret what is consumer surplus, is to realize that if you graph p of x, if you graph p of x, and then you think of the market price p as just being a straight line across, then the consumer surplus is that, since you're finding an integral, the consumer surplus is that area. So that's like visually, that's a helpful way to actually see it on a graph. Okay, so the next example I want to talk about is from physics, fluid pressure. So roughly speaking, fluid pressure is when you go underwater, it's that force you feel from the water. That's an example of fluid pressure. So now, aside from saying, yeah, I really feel the water pressing on me, that's the idea, but how do we define that in math or physics? So let's talk about that right now. Okay. So the hydrostatic pressure of an object at a depth h in a liquid with density W is P equals WH. Okay. So first of all, hydrostatic, it's a fancy sounding word. It's not that fancy. What does it mean? Hydro, liquid, static, standing still. Okay. And let me see. Oh, no. So pressure is defined to be force divided by area. So it's force per area. So P equals F divided by A. So now we can note that force equals pressure times area, but we know what pressure is. So force equals WHA, density times the H. I'm using H from height, but really I'm thinking of it as the depth, and A is area. So what does this look like in a simple case? Okay. So let's say a plate with 8 square meters of area is lowered to a depth of 12 meters in water. And water has density W equals 1,000 kilograms per cubic meter. What's the pressure on the plate? What is the force? So let's do it. Okay. Okay. So I'm going to calculate the force first because it's the easy, straightforward thing. So force is just WHA. The density is 1,000. H is the depth,
12.
which is 12. And A is the area, which is 8. And so it all works out to 96,000. Right. And we know that our units for force are newtons. Or we also talked about it as being joules per meter, but that's not, we don't need that here. Newtons is fine. Okay. So there's the force. And alternately, what's the pressure? So you could,
Divide by 8.
yeah. Right. So we also said earlier that pressure is just WH. So that's just density is 1,000. The H was 12. This is 12,000. Okay. Right. And it's force per area, so you could do newtons per square meters. Okay. So I don't expect you to immediately see what the units are, but I'm filling in the units because I like to have them there. Okay. But as far as calculation go, that's how you can find force, that's how you can find pressure. Okay. So, let me just make one comment. When we think of depth, depth is going down. So technically, if you were graphing that, you might call those negative numbers. I'm going to use the convention where I say a depth of 1 is just 1. So I'm going to think of depth being positive. I'm going to be consistent throughout the whole problem, so this is okay. Alternately, you could say a depth of 1 means y is negative 1, and that would be okay. But I'm just going to say a depth of 1 means y is 1, and I'm going to be consistent throughout the entire problem. So either way. Okay. So now we're going to talk about the hard case. So this was an easy case because it was linear. The density is always the same, the depth is always the same, and the area just is what it is. But what if the depth is not the same for your entire object? So for example, if the plate is vertical, then your object is vertical, then it's not all at the same depth. And what if it's not rectangular, so the size is varying? So, suppose you have a vertical rock with a flat face, and it sits in the water. At a depth of y meters, it has the width 0.4 y. For y going from 0 to 2. What is the pressure on the rock? So, what's going on here? How do we understand this?
Pressures change.
So you go from 0 to
Yeah.
2.
So different parts of the rock are sitting at different depths. And as we know, that means there's going to be different amounts of pressure at different parts of the rock. So if the pressure is changing, what are we going to do?
Add all those up.
Add them all up. Exactly. So pressure is constant at the same depth. So if we want to have something that's at the same depth, we take a horizontal slice. And of course, horizontal slices are defined by us by saying that's delta y or dy. Exactly. So for that slice, what is the pressure? Yeah, let's put it all together. So to find the pressure, first of all, we need the depth. So for a slice, so what's the depth? The depth is just y. First of all, then what's the, so remember we're doing WHA in some order, okay. So the depth is y. What's the area? Well, the area, it's a slice, so it's a rectangle. So the area of a rectangle is length times width. So what is the length of that slice? Yeah, it's whatever the function says it is, which in this case was 0.4y. And what's the width of that slice? It's dy, or delta y. And as we said before, this is water, so the density is W equals 1,000. So the total, sorry, that should say pressure. Oh, no, that's force. That's right. Sorry. Okay. Okay. Fix that. Okay. So So, we know what the force is on a little slice that's delta y or dy. So if we want the total force, we add up all the little forces. Force is WHA. So the force in this case is adding up all the little forces. So on each slice, the force is the density times the depth. Density 1,000, depth y, and area, which is 0.4y times delta y. And of course, if we want it, and that's an approximation. If we want this to be exact, it's an integral. In this case, an integral from 0 to 2. Fix that. Okay. And so that is the source of the general formula. So in here, I put the depth is h, but typically, except in some strange situation, the depth is going to just be y. So you could almost make this w times y times f of y dy. So let's use that to do this problem. Okay. So we've got a right triangular plate. And that right triangular plate has a base of 4 meters. Which is 4 meters below the surface, and the tip is at the surface of the water. So how do we find the total force? So what should we do to start? Okay. So I don't know about you, but I can't figure anything out unless I draw a picture. So here's the surface of the water. What's the plate? What does the plate look like? Right triangle. It's got a base that's 4 meters long, and it's sitting, and the base is 4 meters below the surface, and then that's the tip. So like this. Okay. So there's the plate. Okay. So how do we find the force? It should be the integral from 0 to 4 of W, H, and then this is going to be A, but we know since we're integrating, we need to break this up as, I guess, let's see. Really, this is like width, but I already used W. Darn it. All right. So I'll just say L. I'll say length across of Y dy. Okay. So integral from 0 to 4. What's the W? What's the density?
1,000.
Yeah, it's water, so it's 1,000. Okay. Now H represents the depth. So what is the depth at any spot? It's just Y. Okay. Now at any spot, what is the length across? Really, we think it is the width, but what's the length across?
It will be a negative slope or
Right. Well, here's a simple little check. When the depth is 0, what's the width across? When the depth is 4, what's the width across?
just negative x.
So what do you think? The length across is just Y. Let me ask you this. At a depth of 2, what do you think the length across is?
Better not be 2.
Can we use common sense and look at the figure and make a guess?
The area of fence.
Are we asking about lengths or areas? We're trying to figure out what the length is. Because remember, you know what I should draw? I'm going to draw this, and this will be very helpful. When we constructed this formula, what did we talk about? We talked about a slice that's dy. So what we need is, we already know the density, we know the depth of that slice. The depth of that slice is just whatever the y value is. We also need the area of that slice. The area of that slice is whatever its horizontal length is times dy. So the question is, what's that horizontal length? We need to figure it out because it's clearly varying. So I'm asking you, when the depth is 0, what's the length across? 0. When the depth is 4, what's the length across?
4.
So take a crazy guess. When the depth is y, what do you think the length across is? It's y.
Because it's y equals negative x.
So there you go. And so someone pointed out that one way to see this simply directly algebraically is the following thing. What we've done is we've decided to call this part of the y-axis the positive part. As I mentioned before, I'm treating all depth values as positive. So those are like positive y values. This surface level is like the x-axis. So if we reorient this, so this is positive y and this is positive x, we're starting, what we're really doing is drawing that. So that when the depth is 0, the width is 0. And then when the depth is, when the depth is 4, the length across is 4. So what is that graph? That graph is just y equals x. Now it's positive y equals positive x because I put positive y on the bottom, which is a little weird, but that's what we're going to do because we talk about depth. Okay. So another way to figure this out would be to say this is 0, 0. What point is that? 0, 0. What point is that? At a depth of 4, the width is 4. And you can make the equation of a line out of those 2 points. So there's several different ways to construct this. You could use 2 points and then build the equation of a line. You could simply just talk about a bunch of different values and sort of realize, oh, whenever the depth is y, the width is the horizontal length is the same thing, so it's just y. Or you could think of it visually as the graph and realize it's at a 45-degree angle, so it's just y equals x. But that does give another good way to think about this, which is that this is really the length across, so this is represented by some kind of x value. Now in this case, y equals x, so it's just y. But in general, because you're trying to measure a horizontal distance, you're measuring whatever x is. So in the previous problem, what was x? X, where is it? In the previous problem, x was 0.4y, so that was your horizontal distance. Okay. Anyway, I don't think it's reasonable to give you geometrically complicated ones. This will generally be relatively straightforward. Not that it's easy, but it'll be somewhat straightforward, and hopefully you can get it from there. So to finish the calculation on this problem, integral of 1,000 y squared dy, which is 1,000 y cubed over 3 from 0 to 4. So that'll just be 1,004 cubed over 3 minus 1,000 0 cubed over 3. And that's just 21,333. And this is force, so it's newtons.